Welcome back. In this next brief video, I want to explain to you why demand-driven analysis are not just more efficient than exhaustive analysis, but that in some situations they can also even be more precise. And that's really exciting because you can have the most precise exhaustive analysis in the world. If you make it demand-driven, there can be a chance that it's even more precise than that exhaustive analysis on its own. And I'll here be using the example by the same authors from their paper. And here we are assuming that we have a certain baseline analysis that is not already very precise by itself, right? So here they deliberately used some analysis that is not the most precise one in the world, so that we can actually improve over its results. So the assumptions here is that, first of all, this is a program in a Java-like language, and we have the given class hierarchy. So X is a superclass of Y, which is a superclass of Z, okay? And this field F here is actually declared in X, so it's a field that's accessible in all these three classes. And also, we're assuming that we have an analysis that is type-based. So that means we have a pointer analysis that represents allocation sites by their runtime type. Okay, so in particular here, these two allocation sites, they're actually being represented by the same identifier, by the same type identifier X. So we have a single node representing these two sites. That's why I mean this is not the most precise baseline analysis in the world, right? So as you know, in Spark, for instance, we would be typically distinguishing these two allocation sites, but I also explained to you earlier that there are these type-based representations where you are unifying these two alloc sites into one, and that's what's happening here. Now, the demand that we have in this program is that we want to resolve this virtual function call here. And this function is actually also declared in X, Y, and Z. So that means without knowing anything else, this function call might actually be going to x.vfun or y.vfun or z.vfun, right? And that's exactly what we want to figure out using the analysis. Now, the thing is now, if you do a demand-driven analysis here, then you will figure out the following, right? So you will figure out that T comes from x.f, right? And now X is being initialized through this allocation site here, okay? So X points to this type-based representation X, okay? And we also know then that x.f, which is initialized to Y, it points to this type-based representation Y, right? So this is the allocation site for the field, basically, or the field's value. And this is the allocation site for X itself, represented by their types. And then T, because it points to x.f, right, it's also pointing to that same node here. So that's the representation that you get in the demand-driven analysis, and that's sort of what you would expect to get in this case, right? In particular, there's no aliasing with this variable small y or anything like that, okay? So that's because we basically do the demand-driven computation like you see here, right? So it starts down here, and it's then working its way backward along the definition use chains. And yeah, the same here actually for the field up here. Now, the thing is, if you do an exhaustive analysis, this looks different. You will get less precise answer actually. And in particular here, we will now get the result that both X and Y, they can point to the same allocation site, because here we have this type-based representation, right? So both this alloc site and this alloc site, they're both represented by the same node. And that's why the analysis, when it does this exhaustively, right, it considers this statement and then this statement, and it will then basically give you already this part of the graph, right? So we'll assume that they are both aliased. And now this unfortunately means that also here, when you have this field, these two field initializations here, right? why they actually point to y and z, we now get the result that here t might actually point to any of these, right? Because when we process this statement, well, we assume that x, when we resolve this, actually points to this, but y also points to this, right? And so basically we don't know anymore when we access this this f here, right? So we basically, through x, we get here, but then we follow these f links. We don't know anymore whether we should end up here or here. So therefore t it actually also points to both of these alloc sites here, or both of these representatives. And that's obviously less precise than what you have here, right? And so the problem that you have here is, if you look into this closely, is that we're actually considering alias relationships that in this particular program, using this particular representation, are possible, right? So at least, by what the analysis assumes through its representation, it assumes that these alias relationships are possible, and therefore they creep into this result here, right? So they make it imprecise. Whereas in the demand-driven analysis, this does not creep into the result because anything related to y is not even relevant, right? It's not even considered. And we know this because essentially of this statement here, right? So this statement is telling us that x matters, right? And by going backwards, by computing this demand, we can figure this out, right? But by doing an exhaustive analysis without having any demand drivenness, we don't have that information, right? So therefore we can't really filter this here. And in particular, therefore we get this edge here into the result, and that's what's messing up the precision in this case. So in the exhaustive analysis, you basically have these forward propagations here, right? And they make this imprecise. Yeah, that's all that I wanted to tell you about in terms of the precision of demand-driven analysis. So that was just one example, right? But there are many more that show you that demand-driven analysis can be more precise than exhaustive ones. And that's actually also something we have really seen empirically in our studies, right? So we've done a number of empirical studies using Boomerang, but also other more recent approaches that I will still be talking about in this course. And we really saw a very high precision. And some of these algorithms that I'm explaining to you here, they're also now going into actual products, right? So I briefly talked about CodeShield and our spin-off company and the product that we are developing there. But we are also currently teaming up with other leading static analysis tool vendors that are picking up these algorithms because, well, they believe us, and we were also able to empirically show that they have really many advantages, in particular when it comes to conducting demand-driven security code analysis. In the next chapter, I will be talking about some other static analysis called flow twist, which is sort of demand-driven, but not quite, but it also shows the limits of the kind of demand-driven algorithms that I just explained to you. Stay tuned for more.